So the complexity of a topological sort. Now remember, I've gone over all about the space requirements and the data requirements of this. Now comes the complexity and time. And I want to make sure it's not obvious. We know V is vector, E is edges, that part's obvious. But I want you to notice here is that there's going to be some speeds here, O of E plus V. It looks simple enough saying, oh, it's going to be super fast. But there's a problem with this. By the way, this little segment was some extra code that I saw in another version of creating this. Just leave it there for now. But I want you to focus on what's being highlighted right now. And I'm going to first go with the best case. Now, in the best case, the graph is a tree. The whole darn thing is connected. We start at the top of the tree and we get to all of the other vertices. Now, here's the thing though. It's O of all the edges. Now, if this is a sparse graph, that's pretty quick. But it's a super dense graph. It's going to take a long time. Could be n squared, because remember, let's pretend we're doing this in a matrix. You know, let's say everyone's connected to everyone. Man, you're checking all those edges. It's going to take a while. So again, it looks simple enough, but it actually can get worse. And you saw an example of this where it actually has some disconnected portions of it. It's still a graph, but it's disconnected, or in this case, it's undirected and not connected. So here you have to worry about the edges themselves already, and then checking everything and all that good stuff. And then you have all of your vertices. You actually had a similar example of this when it was disconnected. Remember when that stack had to restart all over again, then you started with the next lowest number to start your DFS? That's really the vertice portion of this. So you could add extra work to it. So that's the differences between the two in your code complexity.